So we are looking at strategies, sort of modern strategies for generating elements or generating shape functions and strain displacement relationships in elements. Um, so suppose we have a scalar field variable phi of x. For simplicity, assume that we just dealing with this, and then we will interpolate it as um, phi equal to n1 phi 1 plus n2 phi 2 and so on, depending on how many number of nodes your element has. So if it has 3, then it will be 3 as in the 3-noded triangle. If it has 4, it will be n1 n2 n3 n4 as for q4 and so on and so forth. So this can be written as a shape function matrix as we have done before, and a function and a vector of the nodal values of phi. So this can be written as n times, let's say, capital phi. Capital phi is the list of nodal values of phi for that element. Now suppose I interpolate the coordinate. So I have this element, let's say this element flanked by nodes 1 and 2. So I interpolate phi in this way, the field variable, depending on the value of phi 1 at node 1 and phi 2 at node 2, and the position of a point which is given by x from some coordinate axis is interpolated in terms of x1, which is the coordinate of point 1, and x2, which is the coordinate of node 2. So this interpolation we do using another set of interpolation functions which we call n1 cap, n2 cap, and so on. So potentially these two interpolating functions, these two interpolation schemes can be different. Now, if each ni is equal to ni hat, we call the interpolation isoparametric. The elements are isoparametric elements. If the degree of n1 is greater than the degree of n1 hat, it is called subparametric, and otherwise it's called superparametric. We are not going to deal with subparametric or superparametric, which we will deal with the isoparametric interpolation scheme only, in which case x will be given also by n1 x1 plus n2 x2 and so on, which means that the coordinate value as well as the field variable are interpolated in exactly the same way using as many number of shape functions as there are in either. Okay. So we will discuss the isoparametric scheme only. Now, before we go into the details of the isoparametric scheme, mm, things are somewhat easy in 1D, because in 1D we can we have this thing called the Lagrange polynomial, which is a scheme for interpolation in 1D, and this gives me directly a formula for generating shape functions. So if you look at this polynomial, this is a polynomial. So I have let's say n number of nodes which have coordinates x1, x2, xn, 1D element, and values at those nodes are phi 1, phi 2, and phi n. These are known to me. Then to find the shape function value at any point, I use this particular polynomial. If you see this polynomial, it automatically satisfies the properties, all the properties of the shape function. So if I put xk, so this is nk, so if I put xk here, so this will all become k, and then you see the numerator and denominator become the same, and this, the value of this is 1. In place of xk, if I put, let's say, x1, then this term will go to 0, and therefore this will be equal to 0. So this if you generate nk through this formula, then it will obviously satisfy the Kronecker delta property. Now we can do this for element with 2 nodes, and we will write the shape functions directly as n1 as x2 minus x by x2 minus x1, and n2 as x minus x1 divided by x2 minus x1. So if I put x2 here, this is 1. If I put x1, this is 0. Here, if I put x1, this is 0. And if I put, if I put x1, it is 1. If I put x2, it is equal to 0. So uh, these are generated right away from the Lagrange polynomial or the shape function. So this is one way in which you can generate functions, shape functions, through through directly generate them through Lagrange polynomials. So if you look at a three-noded linear element with 1, 2, and 3 being the nodes, then the shape functions are like this. So this is for node 3. This is the shape function n3. This is the shape function n1. And this is the shape function n2. So the interpolation property is this one is 1 at 1, 0 at 2, 0 at x2, 0 at x3, 1 at x1. So Lagrange polynomials will directly give you this shape function. N2 is this 1 at x2, 0 at x1, x3 will give you this. N3, 1 at x3, 0 at x2, x1 will give you this. So directly you have the shape function, and then this is your actual approximation for phi of x, which is n1 phi 1 plus n2 phi 2 plus n3 phi 3. So this is what we will have for Lagrange polynomials. Now, in some cases, even for simple 2D situations, 2D elements, you may be able to generate the shape functions using simple Lagrange polynomials. So consider this element, which is a rectangle. This is a rectangular element. Let's put the coordinate axis at the middle. So this length is 2a, this length is 2b. So this point is and this is minus a plus b. So these are the 4 points. This is local numbering is 1, 2, 3, and 4. So if you look at these shape functions, suppose you look at n4, which is at this node, it will be this tent-like shape function, which is 1 at node 4, 0 at node 1, 0 at node 2 and 3. So this shape function can be generated by using a bilinear function. So you take one Lagrange polynomial along the x-axis, another Lagrange polynomial along the y-axis. So you take one along this, you take one along this, and multiply them together, you will get n4. So this a minus x divided by 2a is a minus x divided by 2a is the shape function, is the Lagrange polynomial along x direction, and b plus y divided by 2b is along the y direction. Multiply them together, you get n4. And similarly, bilinear shape functions can be derived from for n1, n2, n3, n4. Also, for simple rectangular situations, for simple rectangular elements, you have shape functions which, as I mentioned earlier, contains the trial functions 1, x, y, and xy. So the complete polynomial is still 1, and there is this incomplete second order polynomial term xy in the trial functions that you can see from here. This has b times x, a times y, uh, ab, and then xy plus xy. So these are the 4 terms that are there in this rectangular element. But obviously, if you want to go to more complicated, more general shapes of elements like triangles or arbitrary triangles or quadrilaterals, this will not work. This will, however, work very well in 1D, as we have seen, but for more than 1D, except for very simple shapes like triangles, like rectangles. I'm sorry, it's not going to work very well. So we have to look for a better strategy, and that's what I'm going to tell you about now. Now, here is the idea that was first proposed in this paper in 1966. And the idea is this. Suppose I have a physical element which is there in your mesh, which is a quadrilateral flanked by four uh, nodes. So they are numbered 1, 2, 3, 4 as shown. Now, this element can be mapped. This element lies in the xy coordinate system. It can be mapped from a standard parent element which lives in a different coordinate system, which we have called the RS coordinate system. And this is a topologically similar element. It is a square of sides 2 each, and we envisage this physical element, we imagine this physical element as a mapping, one-to-one mapping from this parent element to this physical element. So what we are going to do is node 4 we are going to place on node 4, then we are going to stretch this edge for node 3 to match, then we are going to stretch 2 3 to match node 2, and finally node 1. So this is a stretched, compressed and distorted version of this standard parent element, and it will turn out that for many cases like quadrilaterals, hexahedrons, tetrahedrons and triangles, we can easily design a parent, a standard parent from which we will generate the physical elements. Now, one-to-one means that every point in this parent element is mapped to one and only one point in the physical element. So this point here is mapped onto this point here. Every line, this line in the RS coordinate system, this line is r equal to minus half, r equal to minus half. So this line r equal to minus half is mapped onto this line here. Similarly, this line is s equal to plus half, and that is mapped into this line here. This line is uh, is your s equal to 0, and this line is s equal to 1. So this forms the edge of the element. So this forms the edge of the element as well. This line is the map of the top edge of the parent. So top edge of the physical element is the map of the top edge. The right edge is a map of the right edge of the physical element, or the other way around. The right edge of the physical element is a map of the right edge of the parent element. So this is for a four-noded quadrilateral. For other cases, we can have, for different other cases, we can have other kinds of parents defined. So we will see what is the advantage of defining a parent. The advantage of defining a parent, in short, would be that the domain of a parent is fixed. It's always 2 cross 2. So if we want to do integrations, we would rather do them on the RS system rather than on the XY system, because this has then the integration will be over a fixed domain, and that fixed domain integration can be standardized by using very well known numerical techniques. So that is what we are going to do. Now, in the RS system, if this is your parent element, we have already done the rectangular element. We have already done the shape functions of the rectangular element. And now for this rectangle, which is a square, you know A and B both are equal to 1. A and B are equal to 1. So you simply put in place of A and B, you put 1, and you get the shape functions in the RS coordinate system, the 4 shape functions for the square element that we have. Now let the coordinates of the physical element be known. They would be known: x1, x2, x3, x2, x3, and so on. X1, y1 plus x2, x1, y1, x2, y2, x3, y3, and x4, y4. So by the isoparametric assumption, we use this same shape functions to interpolate the positions as well. So x at any point and y at any point inside the parent element is obtained by the same using the same shape functions as they are used for the field variables and the nodal coordinates of the four physical nodes of the element. So this is by dint of the isoparametric assumption that we have made. The displacements, this would be u and this would be v. So the displacements are interpolated in the usual manner. This is a cut and paste problem which I will fix before I upload. So this is how the displacements will be interpolated. The same set of shape functions will be used to interpolate the coordinates as well. Now this is the mapping of the element. This mapping is the one-to-one mapping that I'm talking about. So if you put, for example, r equal to 1. Okay, let's go back to this. If you put r equal to 1, then you are talking about this edge. This edge is the r equal to 1 edge. Let's see where it goes. So if you go back to this and put r equal to 1, this becomes 0. This becomes 0. N2 becomes half into 2 into 1 minus s, and this becomes equal to 1/4. Sorry, this becomes 1/4 into 2 into 1 plus s. So this would be half 1 minus s, and this would be half 1 plus s. Now put it back into the mapping. X would therefore be equal to, only n2 and n3 are non-zero, s would be equal to half 1 minus x x2 plus half 1 plus s x3. Y would be half 1 minus s y2 plus half 1 plus s y3 for the line r equal to 1. So the line r equal to 1 will be mapped onto a line in a physical system which has x and y given in terms of this s. So when s is equal to let's say 0, this would be at half when s is equal to 0, which means on this line you are at this point, then you would be mapped to half x2 plus x3. That means you would be mapped to half x2 plus x3. That means you would be on this line that bisects this 2 3 line. So you would be here, and y would be half y2 plus y3. So this point here would map exactly to this point here. When s equal to 1, this would become 0, and you would be mapping to half x3 half y3. Sorry, x3 y3, not half. X3 y3 would be mapping to x3 y3. S equal to 1 is this point, so this point will map onto this point. Similarly, this point would map onto this point. This would map onto this. This would map onto this. So this is how the mapping will work, and the mapping is one-to-one and well defined. So this is the mapping of coordinates from RS. If you know the RS coordinate of a point in the parent, you can find the XY coordinates of the physical element using these set of equations. Okay. Now, how do we find the derivatives? Now, if I know a function, if I know the mapping x as a function of r and s, y as a function of r and s, Then the question is, if I have another function phi, which is a function of x and y, which are in terms functions of R and S, how do I calculate, let's say, del phi del R? Or how do I calculate del phi del x? So this can be done through a chain rule. So del R of any quantity would be del x times del x del R, del x del y times del y del R. This would be del R. Similarly, del s would be this. So these are transformation relations for the gradients del R and del s in terms of del x and del y, and it can be written, this operator equation can be written as del R del s is equal to what is known as the Jacobian of the transformation. This is the Jacobian of this mapping, and times del x del y. Now this mapping is known in terms of the shape functions. So del x del R can be easily calculated and would turn out to be, so remember, x is equal to summation of ni xi, where I goes from 1 to 4 in case of the Q4 element. So del x del R. So these are functions of x and s and r. So this will be del ni del R times xi. So that's what you have here. Similarly, uh, this similarly derivatives with respect to s. So this will be known, this Jacobian would be completely known once you have the shape functions in place. So this Jacobian is already known. Now, to calculate strains and quantities like that, we need, for example, epsilon xx, we would need del u del x. So we need derivatives with respect to x. Here what we have is derivatives of r and s in terms of derivatives of x and y. To get this in terms of these, which are easy to calculate from these relations, we will have to use the inverse relation, that del x del y would be equal to J inverse del R del s, where, as I said, J and J inverse are known functions. If J is known, J inverse is known as well. Now, this is the relation that we are now going to use to calculate all quantities which depend on the first derivatives. So we'll give J inverse a name. We'll call it gamma. J inverse is called gamma. And in 2 dimensions, the determinant of J will be given by J11, J22 minus, that's the determinant, and we will call the determinant of J as just J. Now, this determinant has a physical meaning which you might already know. For a mapping which is x as a function of Rs and y as a function of another function of Rs, if you know this mapping, the determinant of this mapping gives you the ratio between an infinitesimal volume xy to the same volume in the mapped coordinate system. So J relates these two volumes. In other words, J times dr ds is equal to dx dy. Or in 3D, J times dr ds, and if you use the other coordinate in the parent system as t, dr ds dt would be equal to dx dy dz. So J, which is the determinant of the Jacobian matrix, is important for us because it is going to relate the it is going to aid us in changing the variables of integration from xyz to rst. Now, two things are important here. One is, if J is equal to 0, then we are basically saying that volume dx dy in the parent coordinate system basically shrinks to 0, shrinks to a point, which is not possible in a one-to-one mapping, and therefore we will require mappings for which J is strictly greater than 0. J can not be even be negative which means that the sense of dx and dy and the sense of dr and ds. So if dx is increasing this way, dy is increasing this way, dr also must increase this way and ds must increase this way. So if that doesn't happen, you might end up with a negative j. So if there is a flipping of this element as you go through this mapping, if there's a flipping of this element, flipping of this infinitesimal element, then you might end up with a negative j, and that situation also must be avoided because flipping might cause a situation like this. So you have a parent element which is like this: 1, 2, 3, 4. These are the nodes, and when it if areas flip, then you might have a situation where you have two. So you have an element like this, which is not desired. So the mapping cannot lead to a flipping of the element as you go from the parent to the physical or the physical to the parent. So we will, the long and short of it is, we must always have j greater than 0 in our calculations. Our mappings, our shape functions, everything has to be defined in such a way that j is always greater than 0. Okay, so now that we have the relation between the derivatives, we can now, in a problem in elasticity, we can now go ahead and form, let's say, epsilon xx. So epsilon xx is del u del x. That is what epsilon xx is. And del u del x, so if you go back, del u del x would be j11 gamma 11 del del r plus gamma 12 del del s. So we will write it as gamma 11 del u del r plus gamma 12 del u del s. So this would be your epsilon xx now, in terms of del u del r and del u del s. And this, remember, is given by ni comma r ui, and this would be given in terms of ni comma s ui, and ni comma s and ni comma r are the derivatives of the shape function with respect to r and s, which can easily be calculated because the functions, shape functions, are known in terms of r and s. So this quantity and this quantity can be easily calculated. Now if you can work out all the strains, so remember, in two-dimensional problems, this is how we stack the strains in the Voigt notation. If you now calculate all of these, that means you calculate del u del x, del v del y, and then del u del y plus del v del x. If you do this, then and relate it to the ui's and vi's, and ui's and vi's are stored as u1, v1, u2, v2, u3, and so on. If this is your storage scheme, then this would be your B matrix. Please verify this. Calculate each of these terms in terms of the derivatives of the shape functions with respect to R and S, and verify that this is your B matrix. Now, once you have this B matrix, your job is done, because your stiffness matrix is integral over the element of B transpose C B dV. So we have the B here. The C is a constant, depends on plane stress, plane strain, axisymmetric, or three-dimension, whatever your problem is. And B transpose is also known. So you can calculate these. You can calculate KE. You can calculate KE quite easily once you have the B. Now, how do I do this integration? That's what we are going to talk about next. Now, before doing that, here are some examples for 1D elements. So I have written this table for a maximum of 4-noded 1D element. So for a 4-noded element, let's say N1 will be will be a polynomial that is 1 here, 0 here, 0 here, 0 here. This would be your n1. n2 would be similar. n3 would be 0 here, 1 here, 0 here, 0 here. So this would be your n3. Now, if you number it like this and you place the nodes at r equal to -1 and r equal to +1, then at 1/3 distances, then these would be your shape functions. If node 3 is included, these are the terms that you have to add. If node 4 is included, these are the terms that you have to add. And you can include either or both. And this table, there are tables available for many such situations. This table will give you the shape functions that you must choose depending on the number of nodes that you use to discretize your element. Similarly, for a 2D element, 2D quadrilateral element, this would be mapped from quadrilateral. So these are, this is the node numbering that has been used, 1, 2, 3, and 4. So with this node numbering, we can add some mid-side nodes also, which are 5, 6, 7, and 8. So if you don't have mid-side nodes, then 5, 6, 7, 8 are not there. So you don't need to worry about these terms, and you don't need to worry about these terms as well. So you will only have 1, 2, 3, 4, which are the ones that we have already seen, in which case these edges are straight edges. However, if you add these nodes one by one, and you can even add this middle node 9. If you keep adding these nodes, then you will have to include these terms in 1, 2, 3, 4. So these terms will come in 1 if you add node 5, and if you have node 8, this will come in, and then you will have shape functions for node 5 and node 8 as well. For node 9, this would be the shape function, and you can verify this, verify the Kronecker delta properties for each of these. Similar tables have been derived for many situations, as I said, and for rectangular as well as triangular elements in both 2D and 3D. So we will not bore you with many more of this, but this is a very compact way of formulating shape functions, and most commercial codes have several of these already built into their codes.